video, we're going to look at non-random sampling. So the references here are these chapters by Amemiya, and then the Mansky and McFadden book, and then there's a old Mansky and Lerman Econometrica article about how to adjust for non-random sampling in binary choice estimation. Okay, so this is a very common issue. Data sets are often non-randomly sampled. Okay, so different types of sampling. So random sampling, censored sampling, truncated sampling, and then just more general types of non-random sampling. And we're going to look at all of these different types of sampling situations and, what can you do if you're faced with a non-random sample. Okay, so other types of non-random sampling are, say, exogenous stratified sampling. So let me give you an example. So the census data, the census, everybody fills out the short form, but then they also give a long form, and not everybody fills out the long form, right? And so when they decide to give out the long form, a lot of times they oversample certain types of people, so they might oversample families with a lot of children, for example. Or the NLSY, so NLSY is a good survey to get to know, NLSY, and that's the National Longitudinal Survey of Youth, and they oversample minorities, right? And the purpose of oversampling, it's really two reasons. I mean, one, you might want to just have more observations on a certain group, but the other reason sometimes is cost, so it's typical for people to oversample high density population areas because it's easier to sample, right? If you're in a city, you can just go apartment to apartment, whereas if you're in a rural area, you might have to drive 30 miles, in between the different respondents. So for cost reasons, you might choose an exogenous stratified sampling. So exogenous stratified, whether it's exogenous or not, kind of depends on what you're analyzing. So if you were analyzing fertility and you had a model of how people choose how many kids to have, then if your sampling was on the basis of fertility, that would be endogenous. Okay, but if you're studying something else, and you're taking fertility as exogenous, then you would consider it exogenous sampling. Okay, and then there's another kind called choice-based sampling, and we're going to look at that today. But choice-based sampling is sampling on the basis of the choice that you made. So for example, in the context of transportation mode choices, suppose that you went to the train station and you interviewed people about their choice of transportation mode. Okay, so pretty much everybody is going to be choosing train. Like if you go to the Amtrak station, they're probably not taking the bus or whatever. Well, actually, there is a bus stop pretty close to our Amtrak, but normally with choice-based, it's basically you go and you interview people that made a certain choice, like train or bus or car or taxi or whatever, and then you gather information on their characteristics. So the probability that they're in your sample is based on the choice that they made. Okay, and then later we'll consider censored and truncated sampling. And random, you all know, random would just be, purely random from the population. Okay, so I think I already kind of talked about these things. Yeah, so estimators, usually most of the derivations that we see are assuming random sampling, So for example, let's say you want to get the distribution of income in the population. And then if your sample oversamples people on welfare programs or something, then of course if you just look at the distribution of income, it's not going to be representative. You'd have to take into account that you're oversampling people that have lower income, right? So usually with data sets, they give you some sampling weights, and you would have to use those weights to adjust for whatever non-random sampling you have. Okay, so we're going to talk about, how you make these adjustments First, in the context of choice-based sampling. Okay, so suppose we want to study transportation mode choices. You gather data at the train station, subway station, and at cart checkpoints, right? So that's one example. Or here, there's another example. If you want to study the effectiveness of a treatment for heart attacks, and you follow people that had that treatment along with a control group that did not have that treatment. Well, I mean, there are some economists that study these sorts of things, like health economists, but this is closer to the type of research I do. Is say you want to evaluate a job training program. You have a group of people that participated in that program and a group of people that didn't. Okay, so your data set might be 50-50, but in the random population, maybe participants are only like 5%, but in your data set, they're 50%. Okay. All right, and if you want to do like a binary choice estimator or something, we'll look at, how you use weights to adjust for this non-random sampling. Okay, so let's look at this notation. P of I given Z is a probability you make choice I given characteristic Z. Okay, and then P star is going to be the probability that you make that choice in a choice-based sample. So maybe in a choice-based sample, half the people took the train, but in a random sample, maybe 20% take the train. Okay, that would be, well, this is conditional and Z means, people with characteristic Z. Okay, so a key thing that we're going to use is that under choice-based sampling, sampling is random within I partitions of the data. So if you condition on the choice I, we're assuming then you sample at random. Okay, but the overall P of Z is not equal to P star of Z. Because let's say older people take the train, and then you oversample people that are taking the train. Well, then, of course, the age distribution in your sample is not going to be like the random age distribution in the population. All right, so let's say we want to recover probability I given Z. So without the star, that means in a random sample. Okay, we observe, these are all the things we have to work with, okay? We see P star I given Z, we see P star Z, you see the distribution of Z in the choice-based sample, and you see P star I. And we can assume that within choice partitions, the distribution of Z is a random sample. So P star of Z given I equals P of Z given I. Okay, that's everything we have to work with. And we're going to look at how we can recover this object. Okay, and basically you can just apply Bayes' rule, actually. So by Bayes' rule, P star I given Z is equal to P star Z given I times P star of I, so we're looking at this here, divided by P star of Z. Okay, and then Pi given Z is, so this is something we don't see, but we're trying to get this, okay? All right, so we can, so this for Pi given Z, you can use the fact that this equals this P star equals the P. So we're going to plug in here, solve for P star Z given I, so we're solving for this, and plugging it in here, okay? All right, and now this denominator here, P of Z, you can divide in this way, and then again we can plug in P star of Z given J, because this equals that, the PZ equals P star, okay? All right, so we've written it like this so far. Well, now from here we're going to use Bayes' rule to plug in for P star Z given J. So see, we plugged in this. And okay, so now you see that to recover P of I given Z from choice-based sample data, we need to know this. Okay. So basically we need to know, so we have P star of J that we see from our choice-based sample. So we need to know P of J. So that's actually the probability in a random sample that someone chooses J. So let's say we sampled people at the train station and subway station and I don't know, at the toll booth for the cars or something, right? So that gives us our P star of J. We know what fraction in our sample is making these choices. We would have to have some information on the probability of choosing J in a random sample. Okay, so you need that like from some other data set normally, because you wouldn't get that from the choice-based sample. Okay, but once you have that, you can adjust for choice-based sampling. Okay, just using these weights. You form the weights, and the weight is equal to the probability in a random sample. This is the weight here, divided by the probability in a choice-based sample. Okay. So if I'm evaluating a training program and I oversample training program participants, this P star, P star might be 0.5, say if half, and then P of I might be 0.05. Okay. And then for the other, because I equals 1 or I equals 2, like either you chose the training or you didn't. So for the other group, it would be like 0.95 divided by 0.5. Okay, so some observations would receive a bigger weight and some would receive a smaller weight. And these are the weights, I mean, something like this is usually what the data set gives you, or like if you have some data set that's not randomly sampled, they usually give you some weights, okay? Okay, so next we're going to look at how to introduce weights to adjust for choice-based sampling when you're doing just a standard probit or logit model, okay? So this is the basic setup for, this is just for a standard logit or probit. And these are the weights that we're going to define. So this is the ratio of the probability you choose one in a random sample, and P star is the probability in a choice-based sample. Okay, so the weights are always this ratio. Okay, and here is the likelihood. Now I should mention that this, the subject matter actually comes from Mansky and Lerman's work. This is an econometrica paper from 1978, so it's kind of an older econometrica paper. All right. So if you take logs of the likelihood and then we pre-multiply by 1 over n, so it won't change what minimizes it, then you can see why these are the weights that you need. Okay, as n gets large, the likelihood is going to converge. Okay, so see, this is going to be 0. This term here is going to be 0 for d equals 0. So this is going to converge to the probability that d equals 1 times the expected value if d equals 1, times the probability d equals 0 times the expected value of this if d equals 0. So that's 0. So it's just going to, this first term is going to converge to this first term. Okay? And this is the expectation with respect to the sample you have. But now if you take into account the weights, right? So the weights, remember, are equal to the ratio of the true probability divided by the choice-based probability. Then this is going to cancel. This part here is going to cancel with the weight. So you're left with the true probability times just the expected value, like without this, because it's conditional on d equals 1. So conditional on the choice, it's random sampling. So we can just plug in this E star, or E in place of E star. So you can see that this log likelihood converges to the same thing that you would get with random sampling. So basically including these weights undoes the choice-based sampling. Okay, so Again, let's look. This is how the weights are included. And usually when you use some software, they just give you a weight option. And these would be the weights, okay? So that people have these weights. Okay. And remember, to do the weights, usually you don't know this. Like, this normally has to come from other data. This weight here, you can actually usually estimate using the proportion. Like, if you don't know this, like you don't know how the sampling was actually done, you can just use the fraction of d equals 1 in your subsample or in your sample. Although when you're estimating the weight, instead of plugging in a known weight, then that's actually going to affect the standard errors of the like you have to take into account that the weight is estimated. Okay. I think that's discussed in the Mansky and Lerman article. Okay, now let's just look in general if you have some non-random stratified sampling, because this just comes up all the time. Okay, so I just wrote down a very simple example. So suppose we want to compute average earnings, and our sample oversamples females. So in the population, say in our sample there are 75% women, but in the population maybe it's 50%. Okay, let yi denote earnings of person I. Okay, and then d is 1 if female, d equals 0 if male. So then the weights would be the ratio of the true probability divided by the sampling probability. Okay, now how do we estimate average earnings? Well, we take, basically this is just the average. See how d equals 1 is going to switch on this part, d equals 0 switches on this part. And then the weight, this is going to converge. This part converges to the probability d equals 1 times e of y given d equals 1. And then we incorporate this weight, because for all these people, the weight is equal to this. And so you can see how this cancels with this, right? This cancels with this for this part, for this second part. So the weights basically undo the random sampling or non-random sampling. So it's not difficult. You just have to incorporate the weights. Sometimes your data set may give weights. So in the end, the weights should actually sum to the number of observations that you have. So this can be an issue sometimes, that they give you weights that are some weird scaling. So you might have to take wi. So what I do sometimes, occasionally, if they give you a weird scaling, because it'll throw off, it depends what kind of software you use, but if you do the weights by hand, you have to have the number of observations be correct. So sometimes whatever weight they give me, I take the weight divided by the sum of the weight multiplied by n to get it to be the number of observations. So, but it kind of depends on data sets. Like sometimes the weights are fine, but sometimes they might have some sort of weird scaling. Okay, so that's the end of well, actually we're going to consider still what to do when you have censoring and truncation. That'll be when we look at the Tobit models.